In this module, the singleton pattern is covered. A very common and pretty simple one to start with. By starting with a very simple pattern, you can already get used to how the modules in this course are structured. I am Kevin, and I'll guide you through this module. First, we will describe the pattern. We will do that with the help of a real-life example, a very typical use case for a singleton, a logger. After that, we will describe the pattern structure and implement it in a demo. Then we'll look into a variation to make the pattern thread safe. We'll continue with learning about use cases for this pattern and pattern consequences, which can be positive or negative. And we will end the module by looking into related patterns. Let's dive in. The singleton pattern is a creational pattern from the well-known Gang of Four design patterns. Creational patterns deal with object creation. The intent of the singleton pattern is to ensure that a class only has one instance, and to provide a global point of access to it. If you've got a few years of experience in our sector and have worked with an inversion of control container before, you've undoubtedly encountered it, as registering a type with a singleton lifetime is functionality offered by almost all of these containers. A very common example is a logger. You typically only want one logger instance for your whole application to avoid multiple instances interfering with each other, which could result in messages being logged multiple times or not at all. Let's put that on a diagram already. Now, we could simply hold the instance of the class in a global variable. But there's an issue with this approach. It doesn't prevent clients from creating other instances of the class. That's a responsibility that's too widely distributed to be reliable. Therefore, through the singleton pattern, we can make the class itself responsible for ensuring only one instance of the class exists. Another option would be relaying the responsibility to another component, like an IOC container, as mentioned. To make our logger class responsible for managing its only instance, we should make its constructor private. Like that, other parts of the code cannot directly instantiate our logger. If you want to allow subclassing the logger, a protected constructor is also acceptable. Next to that, the logger class will contain a method or property in a modern language like C#10 that will return the instance of itself. For example, an instance property with a private backing field. This property is static, which ensures that when multiple instances of the logger class exist, there still will be only one instance of the instance property. When the property getter is accessed the first time, the instance gets created and stored. When it's accessed after that, the previously created instance is returned, thus ensuring that only one instance exists at any given time. It's a good idea to prefer lazy instantiation in this case. When the property getter is accessed the first time, the instance gets created and stored. When it's accessed after that, the previously created instance is returned, thus ensuring that only one instance exists at any given time. The instance isn't created before the instance property is accessed. Next to that, a logger class will typically contain methods like log. These are defined as regular instance methods, so they're not static. They are accessed via the instance property. And with that, we've got our diagram. Let's have a look at the pattern structure. In this part of the module, we're going to map the real-life example we ended up with to the pattern structure. The idea is that this pattern structure can be applied to other real-life scenarios as well. The reason for doing so is that from this structure, you will be able to apply the pattern to other real-life situations. Mapping our logger example to the singleton pattern structure is pretty straightforward. You're looking at the diagram we ended up with. The logger class itself is called the singleton. A singleton defines an instance operation that lets clients access its unique instance. On it, a public static property, instance, exists. A private backing field contains the stored instance value. The log method maps to what is called a singleton operation in the pattern structure. These are operations on the singleton instance. And that's it for the structure already. Let's implement this in a demo. So in this demo, we're going to implement the singleton pattern. As mentioned in the introduction module, project files for all patterns have been added to the starter solution. All of these contain a program.cs file in which we will write the code to test the pattern, and an implementation.cs file in which we will write the pattern code itself. For the singleton pattern, we want to start with a logger class. That's our singleton. To this class, we add a protected constructor so clients cannot instantiate it, but it can be subclassed. The next thing we want to add is a static instance property and a private backing field for that property. This must be nullable. In the property getter, we can then check whether it's still null. If it is, we instantiate and store a logger instance, and afterwards we always return that instance. That takes care of ensuring that only one instance of the singleton class, our logger in this case, exists at any given time. We also add one method, log, for testing purposes. This is called a singleton operation. Every instance of the logger that's returned when getting the instance property has access to it, and it's always exactly the same instance that is being returned. Let's write some code to test this. First, let's see if we can new this up. Logger is defined in the singleton namespace, so let's import that. And apparently we can't. The constructor is inaccessible due to its protection level. So far, so good. What we can do, however, is get an instance via logger.instance. So let's get two of those and compare them. If these two are the same instance and they match the logger.instance property, we write that out to the console output window. And then we log a few messages as an example. Each of these calls should do exactly the same. Let's test this. And there we go. It seems that the instances are indeed the same instance, which means that these three messages written out from the instance1, instance2, and logger.instance variables resulted in exactly the same. So this seems to work. But there's a potential issue with this. Let's learn about that next. We're looking at the implementation of the singleton class. What we've done here is a naive form of lazy initialization. Lazy initialization is the principle that states that we're only going to create an instance of a class once we need it and not when it's constructed. The problem is that this code is not guaranteed to be thread safe. We could go and create our own locking mechanism, but there's no need for that anymore. .NET includes a way to deal with lazy initialization in a thread-safe manner, using lazy of T. When we use that, the compiler takes care of making this thread safe. So let's do that. We add a new static field to replace our static private logger instance. This is of type lazy of T, in this case lazy of logger. And we state that it's read-only because we won't need to change this object during the singleton lifetime. We immediately initialize it, but we initialize it as a lazy of logger. And that does not mean that the logger instance itself will be constructed. Instead, we pass through a method that will be used for constructing the logger when we first access the lazy logger's value property. So we no longer need this old private static logger instance, and we don't need it in the property getter either. Instead, we return the value of our lazy logger. The first time this is accessed, the logger will be constructed using the action we passed through when initializing the lazy logger. Every time after that, the same instance will be returned, and all of this happens in a thread-safe manner. There's no need to change our client code. Normally, when we try this, we should get the exact same output as in the previous demo. And that is indeed the case, and this time we are working in a thread-safe manner. That's it for this demo. Let's cover the use cases for this pattern next. You can use this pattern when there must be exactly one instance of a class, and it must be accessible to clients from a well-known access point. Our logger is a prime example of that. It's also useful when the sole instance should be extensible by subclassing, and all clients should be able to use an extended instance without modifying their code. That is what we enabled by using a protected constructor. Let's have a look at the pattern consequences. There's quite a few consequences to this pattern. Because the singleton class encapsulates its sole instance, it has strict control over how and when clients access it. That's an advantage. It's also better than global variables, because it avoids polluting the namespace with them used for storing sole instances. As the class can be subclassed, which is enabled by the protected constructor, you can configure the application with an instance of the class you need at runtime. Also, in case you change your mind and you want to allow multiple instances, you can achieve that without having to alter the client, because instance management is now contained within the singleton itself. But there's also a disadvantage. The singleton pattern violates the single responsibility principle, because objects not only control how they are created, they also manage their own life cycle. Now, all of this sounds very interesting, but in modern languages you don't often write code like this anymore, as all of this is mostly dealt with via an IOC container. In that case, it's no longer the responsibility of the singleton class itself to manage its own lifetime, but the IOC container takes on that responsibility. Yet, because of its simplicity, it was the ideal pattern to start with. One thing left: having a look at the related patterns. Many patterns are related to the singleton pattern, if only for the reason that they can be implemented as singletons. We'll encounter 3 creational patterns like that: the abstract factory pattern, the builder pattern, and the prototype pattern. They're all coming up in the next few modules. Next to that, the singleton pattern is related to the state pattern, as state objects are often implemented as singletons. Let's have a look at the module summary. In this module, we learned about the singleton pattern. Its intent is to ensure that a class only has one instance, and to provide a global point of access to it. A naive implementation can be achieved with a static instance property and backing field, combined with a private or protected constructor. However, that's not guaranteed to be thread safe. A better implementation can be achieved with lazy initialization via lazy-off-t. We implemented both as an example. Up next is one of 2 factory patterns the Gang of 4 described: the factory method pattern. Let's have a look